Hello and welcome to this video. I am going to present a brief introduction to the basic notions of Kanban system and present an illustrative example on how to calculate the number of containers that are required for a simple production system. The Kanban system is a system that is based on the concept of Kanban, which is a card in Japanese language, and the concept of containers, which are placeholders which hold a percentage of the daily production of one single item. So it is basically a system to control the flow of production in a factory. In general, we attach one Kanban card to its container for items that are going to be produced, and whenever the the assembly line is finishing with that container, then the card is being removed from the container, and this is, as you can imagine, a continuous cycle throughout the day. The objective of using such a system is to design a lean layout in order to minimize waste, either it be on time, on material, or on cost. So waste is not only, let's say, garbage in terms of material, but it might be waste in terms of time or cost. So our goal is to optimize the production flow in a factory by using a lean methodology. Let me present in a few steps the basic idea behind the Kanban system. In general, we have one storage area, we have one fabrication cell, an area that produces or fills the containers, and we have the assembly line that uses the containers in order to produce the final products. So in our storage area, we have some empty containers, and at the same time, we have some Kanban cards for every type of product. So in this simplified example, we have only one product, and we use one blue card to signify that product in empty containers. So what we do is we map the empty container with a Kanban card, and we pass this empty container to the fabrication cell. In the fabrication cell, we can find some operation lines. Each line is taking some containers, and they are filling them with the spare parts that are required. So the fabrication cell is actually filling the containers with the parts that are necessary in order to continue the process. As soon as they fill the containers, they pass them to the storage area in order to be available for the assembly line. So as you can see here, the operations of the fabrication cells have generated have filled some containers. So those containers are waiting in the storage area for the assembly line to pick them and use them. So the assembly line is also can be split into some assembly lines in 2 or 3 or according to our production needs. So each one is picking one full container and uses the components, the parts, in order to produce the final product. And as soon as one container is turning empty, then we pass it again to the storage area in order to be filled again from the fabrication cell and so on. So as you can see here, we are talking about a cycling process that is continuously operating through a cycled approach throughout the day, throughout the operation cycle. One important decision that management has to take here is what is the number of containers that optimizes the process, and of course, what is the number of units that each container might hold. Those two decisions determine the size of production and the inventory level. The more the containers, as you can understand, the different type of inventory we need to keep, and of course, the more the units in every container, the larger the size of the production per unit. In order to be able to calculate the number of containers, we need to use some empirical laws. One of those is the Little's law, which is giving that the working process inventory is a part of, it comprises of two parts, the safety stock and the product of average demand rate multiplied by the average time that a container spends in the manufacturing process. So if we combine some empirical facts, we can derive this formula for the number of containers per part. So as you can see here, we have a fraction. It's not necessary to focus on how we get this fraction, but let's focus on trying to identify those variables. So the number of containers that we are supposed to use is given by the letter K. D is the expected daily demand in units for every part. The average waiting line for the replenishment of parts is given by the Greek letter omega. By the Greek letter R, we have the average time to produce a container of parts, and alpha and C are giving the safety stock and the capacity of the container. So we don't actually need to, I repeat, we don't actually need to find out how we generate this formula, but how to use it. So let's just figure out that the decision that the managerial team will take on A and C affect the inventory stock and the size of the production lot. So those are the managerial decisions that are the most important. Now let's go through an example to see how we work this out and calculate the number of containers required. Assuming that we have a company that produces one single part, for use in a car brake system, which is part of a car manufacturing company. A typical container spends 0.01 day, and we need to express that in a fraction of a day in processing, which means that if I go back here, the processing is what the fabrication cell is actually spending in order to fill one container, and 0.05 day in materials handling and waiting during the manufacturing cycle. So this one is what the assembly line is spending in order to fulfill its own process. The daily demand for the part is 1,000 units. That's pretty clear. And the management thinks that the demand for this part is not certain enough, so they need to keep a safety stock of roughly 10% of its authorized inventory. Now, the question here is that if its container contains 12 parts of this part, how many containers should we authorize? And if there is a proposal to revise the manufacturing by reducing materials handling and waiting time per container to 0.04 days, how many containers would be needed in such a case? Well, first of all, we need to define the variables that we need in order to work out this formula. As we can see here, the question asks how many containers we are actually need in order to fulfill the needs of our production. So the question is asking for the number of containers. So if we check our formula, we are speaking about the variable K. Next, we need to define what is the daily demand, which is given by D, and as we can see here in our problem, it is equal to 1,000. Next, we need to identify the average waiting time for replenishment of parts, which should be expressed as a fraction of a day. In our problem, is being given as 0.05 day. Next, we need to define what is the average time to produce a container of parts, which is the variable named with the Greek letter R. From our problem, we see that this is 0.01 per day, not per day, sorry, expressed in days. Next, we are checking the safety stock, which is 10%, and is being a holding variable A. And finally, we want to clarify the capacity of the container. From our problem, we see that in our first question, the capacity of every container is 12. So if we combine all those numbers in our equation, we see that for the first question, if we perform all the calculations, the number of containers is equal to 5.5. As we said before, the number of containers cannot be a decimal, so we have to round it either to, let's say, the next integer up or down. Well, here, as you can see, we're not rounding down, but rounding to the 6. But sometimes we might select rounding down because if you, depends on the inventory or our operation constraints. So it doesn't mean that whenever I have 5.6, I round up, but it's a managerial decision, as I said before. In the second question, if we replace those numbers, we see that the required number of containers is equal to 4.5, and again, we select to round it up to 5 containers. So I think that I gave you an illustrative example on how to work the Kanban system and the calculation of the number of containers by using a very simplified example. Thank you for watching. Thank you for listening.